Hi, my name is Amy and thank you very much for watching. So we are watching the Patrick Collins Solidity course. It is a 32-hour course and we are 3 hours and 33 minutes into it. I am not using my regular side because my cat is sleeping on my lap and I have my other laptop open because I have been reviewing the offer letter that they gave us. And it's a whole big mess. So I am not super excited about my new compensation because it's less than what I'm earning now, but my base pay is the same, and I guess they're hoping that we don't do the math on everything else. But yeah, mostly my cat is sleeping and I don't want to move things around in case she gets disturbed. So let's just start watching this and see how much we can knock out tonight so that hopefully for the rest of the week we don't have to do it as intensely for 5-6 hours a day. This is super ambitious. I just do not want to be in this environment anymore, and we're heading into a recession, and I want to I want my own stuff to flourish. So if I need to, not have an amazing, it's fine. I'm stressed. This is fine.
We call this fund function. Then what we can do is we can actually fund this contract with a certain amount of ETH or WAY by pasting some value into the WAY value section and then hitting fund. We will now have sent money into our deployed contract, and we can see a list of the funders and a mapping of those addresses and how much they've actually sent into the contract. We can then withdraw the funds out of the contract with a special exception with only the...
I think I left off, I watched the commercial and I backed up a few seconds, and this is just the overview of what we're going to be doing in lesson 4, which I'm half convinced that I've done this before, but I don't want to just skip over it, so.
The person who deployed this contract can actually withdraw the funds back out. Once the funds are withdrawn, the amount of all the funders is reset back to 0. Are you excited? Well, you should be. And if you finish this section, you'll have completed most of the basics of Solidity, and you'll be ready to start making even more powerful smart contracts. We'll be using Chainlink price feeds to actually set the value of how much these people should be able to fund in USD as opposed to just in terms of Ether. We're going to go over a lot of advanced sections here, and I'll let you know what parts might be a little bit harder to digest so you don't have to spend your entire time trying to figure out exactly what's going on. Be sure to use the GitHub repo to your advantage here and the discussions tab to stay connected with other people taking this lesson. All right, let's jump in. So at this point in Remix, you'll have a couple of contracts here. Simple storage, storage factory, extra storage. Maybe you refresh Remix and these have gone away. In any case, make sure that you just don't have any of those tabs open. We're going to create a new contract called Fund Me.
Should I just redo this whole thing? I mean, it doesn't cost me anything and it keeps me engaged. So I just answered my own question because we go to this and we have this stuff. How about I just create a new folder? We'll call it Orig. And we will just move this stuff into Orig. And then under contracts, we will create a new fundme.sol, because I do not remember doing this, and it is here. This should be also in Orig. Thank you. And I'm never not going to copy and paste the Pragma and the MIT license or the SPDX, because why remember things when you can copy and paste it from somewhere else? You know, I think I told people very small channel. Very small channel. Wow. Okay. We'll just do that. And then also look, everything is a chance to publish. And if you don't put it out there, people think you've just disappeared. So I'm sorry I can't, do literally all the things I want to do and also get this course done. But this is also my fault for not making time for this course. What's half an hour here or there? I think Restream's actually going to help me a lot with actually getting this course done, because I've been very hesitant. Like, I don't want to put it on my computer, couldn't make the time, I've been in a bunch of spaces. Excuses. We have excuses. That's what we have. But what I did was just pull this into a new window so that we can have them side by side. That's all I was trying to do.
So let's go ahead and start creating our FundMe contract. Again, we want it to be able to get funds from users, withdraw funds, and set a minimum funding value in USD. This is what we're going to get our contract to do. So first, let's set it up. SPDX, license identifier, MIT. We'll do Pragma, Solidity. We'll do Caret, 0.8.8, and we'll do contract, FundMe. Awesome. And we'll compile, see if things look good, and they do. Great. Let's keep going. So before we actually embark on creating all of our functions here, let's just add the different functions that we're going to implement. So we want a function fund for people to actually send money to. We want a function withdraw for the owner of this contract to actually withdraw the funds that different funders actually give us. And that's pretty much it. These are the two main functions that we want this contract to do. We will be implementing more functions to help facilitate these two functions. But let's get started by looking at fund. Let's comment out withdraw for now, and let's just start with fund. So we want anybody to be able to call this fund function. So we'll make this public. So as we mentioned, we want to be able to set a minimum fund amount in USD. So there's a lot of things to think about here. First thing we probably want to think about is, how do we send ETH to this contract? Whenever we create a transaction on any of these EVM blockchains, there's this value field that we can set. Value represents how much Ethereum we're going to be sending with our transactions. For example, when we transferred Ethereum between our different accounts, we were actually populating this value parameter with different amounts of Ethereum. In fact, every single transaction that we send will have these fields. It'll have...
Sorry for moving you, but my left wrist has been hurting me, and the way that this is, my wrist is at an odd angle, and I don't want to hurt myself doing this course. So there's that.
Of a nonce, or the transaction count, the account, the gas price, the gas limit that we've seen on Etherscan, a 2, aka the address that the transaction is sent to, a value, which is going to be this amount that we're talking about. We'll also have data, which is going to be what we send if we make a function call or deploy a contract, and then it'll have this VRS components. We're not really going to go over these VR and S because this is that cryptographic magic that's happening when a transaction is signed, but just know that that's in there. For sending value, we can populate some of these fields. The gas limit, for example, is populated to 21,000. Data is going to be empty, and then that 2 is going to be the address of the transaction we want to send to. For a function call, we can also still populate the way that we want to send. So we can call a function and send a value at the same time. In Remix, it has a little drop down here for Way, Gwei, Finny, and Ether. We're going to ignore Finny for now, but of course we have our Way, Gwei, and Ether again, where 1 Ether is worth this much Gwei.
Have I bookmarked ETH? Okay.
And this much way. The first thing we need to do in order to make a function payable with Ethereum or any other native blockchain currency is we need to mark the function as payable. It's this payable keyword that makes our...
Okay, so it's public payable, and that's what makes it fundable.
fund function red as opposed to having it normal orange. Just like how our wallet can hold funds, contract addresses can hold funds as well. Since every time you deploy a contract, they get a contract address, it's nearly the exact same as a wallet address. So both wallets and contracts can hold native blockchain token like Ethereum. And you'll see that when we deploy this later on in the lesson, that it actually will gain a balance of Ethereum. Now that we have it payable, we can access this value attribute by using one of the global keywords in Solidity with message.value. To get how much value somebody is sending, you use message.value in your function. Now,
yeah. So there's, I think I looked it up at some point, and there's actually a lot of things that come natively with it's basically like the ABI, like it's a value that is available to you when a message is sent to this contract.
let's say we wanted to set our message.value to a certain value of Ethereum. Let's say we wanted people to send at least one whole Ether with all their transactions. Or put another way, if they sent Ethereum, they would need to send at least one Ethereum. How would we implement that? Well, we could use something called require. We would say we would want to require the message.value is greater than 1E .
That's scientific notation.
18. There's a couple things to unpack here. 1E18 is equal to 1 times 10 raised to the 18th, which is also equal to 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8. This is the value in Wei of 1 Ethereum. This much Wei is 1 ETH. So if we wanted the message.value to be at least 1 ETH or 1 Polygon or 1 Avalanche, etc., we would set it like this. Require message.value is greater than 1. This require keyword is a checker. It says, hey, is message.value greater than 1? If not, it's going to revert. It's going to do what's called revert with an error message. And we can say, didn't send enough. We can try deploying this on a JavaScript VM. We'll deploy FundMe. We'll hit deploy. Look at FundMe. We see this fund button is now.
See, this one, the minimum value has not been reached. How do you...
Red. If we call FundMe right now, and we look at the console, you can see we actually get an error here. Call it again, we get an error. We get an error here. We know that the error is going to be this. Didn't send enough. So what we need to do is we need to send at least 1 ETH with this fund transaction in order for this require statement to be fulfilled. So back up in the value section, we can
Oh. Well, okay. 1.01. Why is this 1, 2, 3, 4, 5, 6? One, 2, 3, 4, 5, 6, 7. Okay. Okay, yeah, so apparently you have to do the value and then do that.
Change this value to 1, so that's going to be 1 ether, or this much Wei, or this much Gwei. Now we can hit fund. Oh, actually it needs to be greater than 1, so let's send 2, for example. Now we'll scroll down, and now we'll hit fund, and we see that that actually passes. The require statement says, if our first section is false, then go ahead and revert with this error. What is reverting? Reverts can be a little bit confusing, so I wouldn't let this section hold you back if it's a little bit confusing. Revert is when it undoes any actions that happened before and sends the remaining gas back. So what does that actually look like? Well, let's say, for example, we get a uint 256, public number. And in our fund function, we said number equals 5. If we were to go ahead and deploy this, let's delete our old contract, deploy this new contract, our number right now is 0, but if we were to call our fund function, number gets set to 5. However, if we call fund and this require isn't met, this transaction would revert and undo setting number to 5. So let's go ahead and look at our logs here. We'll keep value to 0 so that our fund function reverts. We'll call fund. We'll see that this transaction failed because this require ended up reverting, and number is still 0. So then the question becomes, did we actually spend gas? Yes, we spent gas to change number to 5, and then any remaining gas we would get returned by this require. For example, if we had a ton of computation here, we would have need to send a ton of gas with our fund function. But all of the extra gas that we send after this require gets returned to the original user after it gets reverted right here. If reverts are a little bit confusing for you here, don't worry too much about it. We'll go over it in future modules. All you need to know right now is that when you do a require statement, if this first section isn't met, the transaction will be canceled and any prior work will be undone, and it'll send an error message. So cool. Let's delete this number for now, and we'll delete it from the global scope. There's actually another way to do these reverts, which we'll go over later in this contract. So what we've done so far is great. However, we're checking message.value in terms of Ethereum. We're looking for one whole Ethereum instead of $50. We want to check that message.value is greater than some number like $50. Let's go ahead and first set the minimum USD value we want people to send along with the fund function. We can do that at the top of our contract. We can say uint 256 public minimum USD equals 50. Now we have some place to check for minimum USD. We're going to update this minimum USD to make it more gas efficient in a little bit.
I think by the end of this, we're actually using something to look up how much USD is actually in Ethereum at the moment.
Now that we've set our minimum USD, we want to be able to require the message.value is greater than, or let's say greater than or equal to, the minimum USD.
Yeah, I mean, that makes sense.
But minimum USD is in terms of USD, and value is in terms of Ethereum. So how do we convert Ethereum to USD? This is where oracles and Chainlink are going to come into play. The USD value of Ethereum is something that we've assigned outside of the blockchain to each Ethereum or any other layer 1 currency or any other native smart contract platform currency. So in order to get this value that is outside the blockchain, we have to use a decentralized oracle network to get the price of 1 Ether in terms of USD. So before we can continue on here, let's learn a little bit more about the architecture of these decentralized oracle networks and the different solutions that they have so that we can create this FundMe contract in the most advanced way possible. As we've talked about, blockchains are deterministic systems, which means that they themselves can't actually interact with real-world data and events. They don't know what the value of an Ethereum is. They don't know what random numbers are. They don't know if it's sunny outside. They don't know the temperature. They don't know who's president. They don't know any of this information. These blockchains also can't do any external computation. Maybe you have some amazing artificial intelligence model that you want to integrate with a smart contract. Smart contracts by themselves can't do anything with that. As we've mentioned, this is because blockchains are deterministic by design. This is so that all the nodes can reach consensus. If you start adding variable data or random data or values that return from an API call, different nodes could get different results and they would never be able to reach a consensus. This is known as the smart contract connectivity problem or the oracle problem. And this is bad news because we want our smart contracts to be able to replace traditional agreements. And traditional agreements need data and they need to interact with the real world. So this is where Chainlink and blockchain oracles come into place. A blockchain oracle is going to be any device that interacts with the off-chain world to provide external data or computation to smart contracts. However, the whole story doesn't even end there. If we use a centralized oracle, we are reintroducing a point of failure. We've done all this work to make our logic layer decentralized, but if we get our data through a centralized node or through a centralized API, or we decide we want to make the API call ourselves, we are reintroducing these trust assumptions that we've worked so hard to get rid of. We're essentially ruining the entire purpose of building a smart contract. So we don't want to get our data or do external computation through centralized nodes. Those are bad news. Chainlink is the solution here. Chainlink is a decentralized oracle network for bringing data and external computation into our smart contracts. As we mentioned before, this gives rise to these hybrid smart contracts, which combine on-chain and off-chain to make incredibly feature-rich, powerful applications. Chainlink is a modular, decentralized oracle network that can be customized to deliver any data or do any external computation that you like. So, for example, a lot of people say, oh, I can just make an HTTPS call to some API and we'll be good to go. The blockchain nodes can't make these HTTPS calls because they wouldn't be able to reach consensus. If they called the node at different times or they did something else, all the consensus would be broken. So instead, we need a decentralized network of Chainlink oracles to do this. And then in the transaction, this network of nodes will return the data to our smart contracts for us. Now, Chainlink networks can be completely customized to bring any data or any external computation that you want. However, doing the customization can be a little bit extra work. There are a ton of Chainlink features that come out of the box completely decentralized, ready to plug and play into your smart contract applications. What are those features? The first one is going to be Chainlink data feeds, and that's the one we're actually going to be using for our application here. Chainlink data feeds, currently, at the time of recording, are powering over $50 billion in the DeFi world. The way they work is a network of Chainlink nodes gets data from different exchanges and data providers and brings that data through a network of decentralized Chainlink nodes. The Chainlink nodes use a median to figure out what the actual price of the asset is, and then deliver that in a single transaction to what's called a reference contract, a price feed contract, or a data contract on-chain that other smart contracts can use. And then those smart contracts use that pricing information to power their DeFi application. We can see an example at data.chain.link. And you can change networks, you can change price feeds, you can change a whole bunch of different information to see some of the most popular price feeds. Let's look at ETHUSD, for example. On ETHUSD, we can see this whole network of independent Chainlink node operators that are each getting different answers for the price of ETHUSD. They're getting aggregated by the network and then delivered on chain. We can see how often they're updated. These ones are updated for a 0.5 deviation threshold or a few hour heartbeat, whichever one hits first. We can see when the last update was, we can see the number of Oracle responses, etc. We can see the contract address directly on chain. We can even look at the contract on Etherscan. We can see some of the history. We can see all the responses of the different oracles. And then at the bottom, we can see the different users and sponsors keeping this network up. Similar to transaction gas, whenever a node operator delivers data to a smart contract, the Chainlink node operators are paid a little bit of Oracle gas in the Chainlink token. Right now, these users of the protocol are sponsoring keeping these feeds up and are paying the Oracle gas associated with delivering this data on chain. Here's an illustration of what the current model of these data feeds look like. A network of these Chainlink nodes each reaches out and gets the information about an asset and then signs the data with their own private.
I am paying attention. I just have heard this before. I'm pretty sure nobody's watching this with me, but, rewatching. This is interesting stuff. I little don't care except for how it affects me programming. So, I understand this. This is like Kubernetes. Oh, hey, Cat has decided that I bumped my other and was too squirmy. So we're gonna close my work laptop, which I had to open because they decided to expire the link that I was using to review my offer letter. And I'm turning on. Well, first of all, second of all, hold on a second. Sorry, we are. I just bought a cooling fan, and it's helpful to plug it in. I unplugged it, because I was getting up, and I need to move it. I'm gonna turn the fan on because I can. Probably should. There we go. We'll see if this helps with the whole, my laptop gets hot, and it did something weird last week while I was hosting a space. So, anyway, we can place bets on how long it'll take me to stream on the wrong channel. But, here we go.
Good key. In a single transaction, then, one node will deliver all the data with all the different signatures to a reference contract. If that node doesn't deliver the data, another node will send it instead. Reputation is incredibly important when you're a Chainlink node operator. If you miss data updates, if you forget to send transactions, you'll probably be quickly kicked off these networks and have no chance of making any more money in the future. These data feeds are used by some of the largest protocols in the space, such as Synthetics, SushiSwap, Compound, and Aave, with several $1 billion each. We can take a look at an example over at docs.chain.link. Work with EVM contracts. We're going to hit EVM chains, scroll down to data feeds. We'll scroll down to the Solidity section, and we can see an example of an entire contract that uses and reads from one of these Chainlink price feeds. We can even open this up in Remix and work with it in Remix. It looks like this example is reading from a price feed on Coven. The reason we're actually going to use a testnet to see this work is that there's a set of Chainlink nodes monitoring the test network to show you exactly how this works out. Once we get deeper into the course, we'll show you how to actually run tests and work with Chainlink nodes without actually being on a testnet, which will make your development much faster. But I highly recommend walking through this section along with me so that you can see firsthand how this actually works. So let's go ahead to faucets.chain.link/Coven. We're going to switch to the Coven network.
Okay, so faucets, chain.link. That seems about correct. I need to D995 FA. Okay. I just asked for some, but this is the right wallet at least. I'm pretty sure I didn't answer. Okay, well that's a little bit of a break. What was I doing? Besides, having Twitter on my thing during the middle of a stream is probably not amazing.
Work. And we're going to get some code.
I think I'm going to just use Gorelli instead of Coven.
ETH. But remember, look at the network flag and use whatever network is in the documentation. So to get some Coven, we're going to come to the faucet. We're going to turn off test link. We'll just stay with ETH. I'm not a robot.
Are you sure?
And then send request. Once our Coven Ethereum has reached our wallet, we can go ahead and close. We can take a look in our wallet and see that we do indeed have 0.1 ETH on Coven. Now let's go back to our remix. We'll compile this contract. We'll go and deploy this on injected Web3. And again, the reason we're going to use injected Web3 instead of JavaScript VM is that there's no network of Chainlink nodes watching our little fake JavaScript VM. There are a network of Chainlink nodes watching the testnet. So we'll scroll down, we'll switch contract to the price consumer v3, and we'll hit deploy. MetaMask will...
Hold on a second. What are we doing?
watching our little fake JavaScript VM. There are a network of Chainlink nodes.
Am I supposed to have that as a thing on my thing? We'll just keep saying thing until anything makes sense.
Watching the testnet. So we'll scroll down, we'll switch contract to the price consumer v3.
I think... Did I miss...
And we'll hit deploy. MetaMask will pop up, and after a brief delay, we can see our price.
So we were at... Did I do something to fast forward this? Because... Okay, yeah, we did this part. I remember this.
On the data feeds.
So... docs.chain link / docs Okay, so we've got this. We can copy this. And then where does this go? Do we just do like a new file? Aggregator 3. That's not how you spell that, but hey, okay. We will paste this and then
We'll scroll down to the Solidity section, and we can see an example of an entire contract that uses and reads from one of these Chainlink price feeds. We can even open this up in Remix and work with it in Remix. It looks like this example is...
Okay, that's what I missed. We'll rename this to price consumer v3.sol. So this is a thing.
Reading from a price feed on Coven.
We don't need to watch the chain link stuff again. So we're doing
0.1 ETH on Coven. Now let's go back to our remix. We'll compile this contract. Go and deploy this on injected Web3.
Okay, so save. And then injected Aguerli this confirm deployed we have a computer.
And again, the reason we're going to use injected Web3 instead of JavaScript VM is that there's no network of Chainlink nodes watching our little fake JavaScript VM. There are a network of Chainlink nodes watching the testnet. So we'll scroll down, we'll switch contract to the price consumer v3, and we'll hit deploy. MetaMask will pop up, and after a brief delay, we can see our price feed consumer down here, and we can hit get the latest price, which shows us the latest price of Ethereum in terms of USD. You may be wondering why the number looks so weird. That seems like a really large number for the price of Ethereum in terms of USD. And this is because decimals don't actually work so well in Solidity. And we'll get to that in a little bit. There's a decimals flag associated with this price feed address that tells us how many decimals to include with this price. It's also in the documentation. However, I know that this one has 8 decimals. So this is saying the value of Ethereum right now is $3,262. It may, of course, be different when
probably $1,292. $1,293.81. Yeah.
You go ahead and try this. Now, there's a number of things that happen in this contract that I'll explain in our FundMe example, but if you want to take a look now and see if you can figure out what's going on, I recommend you do so. Price feeds are one of the most powerful out-of-the-box decentralized features you can use in your smart contract to level them up, especially for decentralized finance. If you're looking for different addresses of different price feeds, you can check the contract addresses section of the documentation, choose the network that you want, and then scroll down and then look some of the different addresses of the different price feeds. For example, this address will give you the price of 1-inch token in terms of Ethereum. This address will give you the price of the Apple stock in terms of USD, and so on and so forth. The next decentralized application right out of the box is going to be Chainlink VRF, or Chainlink Verifiable Randomness Function. Once we do our lottery example a little bit later, we'll talk about how randomness can be manipulated in blockchain. Blockchains are deterministic systems, which by definition means that they can't have randomness. If you can determine what a random number is, it's not really random anymore, is it? So we need a way to get a provably random number by looking outside of the blockchain. And oracles are perfectly positioned to do exactly that. Chainlink Verifiable Randomness Function is a way to get provably a random number into our smart contract to guarantee fairness and guarantee randomness of applications. Many protocols like Pool Together, Axie Infinity, Ether cards, Avagochis, and more use Chainlink VRF for lotteries, for randomizing NFTs, for gaming, and for more. We're going to do an example of Chainlink VRF in a later section once we get to the lottery section. If you want to see if you can play with the randomness yourself right now, I recommend you going to docs.chain.link, EVM chains, and scroll down to get a random number. And this will teach you how to get a provably random number into your applications. The next decentralized out-of-the-box feature of Chainlink is Chainlink Keepers, which is decentralized event-driven execution. As you've seen, in order to kick off some type of transaction, somebody needs to spend the gas and somebody needs to sit down and hit the go button or hit the transact button or hit the send button. This is obviously a centralized vector if you have a decentralized application that needs to run at specific times or after specific events are triggered. Chainlink Keepers are the solution to this. Chainlink Keepers are Chainlink nodes that listen to a registration contract for different events that you specify to fire. Maybe you say every 10 minutes you want to do something, or once a week do something, or if the price of some asset hits some number, or maybe a liquidity pool is at a certain level, whatever event that you want to code, you absolutely can. The Chainlink nodes constantly listen for these triggers to happen and check the different contracts for these triggers. Once a trigger returns true, the Chainlink nodes will then perform whatever action that you tell the Chainlink nodes to do. We're also not going to go over the Chainlink Keepers examples right now because we're going to get to them in a later module. However, if you want to try them out, go to docs.chain.link/Ethereum, go to Making Compatible Contracts, and feel free to read the documentation and try it out yourself. The last out-of-the-box feature of Chainlink is the most customizable, but also the hardest to get correct. End-to-end reliability is the ultimate promise of our smart contracts, and we want and need them to be able to do anything. We want to be able to take any input and get any output. Making HTTP GET, HTTP POST requests is an easy way to customize our Chainlink nodes to be able to do anything. Remember how we talked about making API calls? That blockchain nodes themselves can't do that? Well, Chainlink nodes can do that. Chainlink nodes can make direct requests to any API that you specify. In order to do this, you both have to choose the Chainlink node and the URL/data to send the request to. This is a little bit trickier than Chainlink VRF, Keepers, or price feeds because you then have to be responsible for creating the Chainlink network that gets data from many different Chainlink nodes and many different data providers. But let's look at an example in Remix anyways. For this section, feel free to just watch since we are working with a testnet here. And testnets, as we've seen, can take a little bit of time. As long as you're familiar with what this process looks like, that's good enough. You don't actually have to try it if you don't want to. So we'll open up in Remix. We'll read
I will not be.
through. It looks like this example is on the Coven network. So we'll go ahead and compile API consumer. We're going to go ahead and deploy on the injected Web3. We're going to make sure that we're back on the Coven test network. We're going to scroll down and we're going to change the contract to the API consumer. And we're going to go ahead and hit deploy. We're going to deploy this contract to the Coven testnet. And now we can call this function called request volume data to actually make an API call. Now, like I mentioned before, whenever we request data from a Chainlink node, we have to pay a little bit of Oracle gas or link token. In order to pay some link token, we're going to need to have link token in our API consumer contract. This is what's known as the basic request and receive model. To get link token, we go back to our faucet, and this time we'll select 10 test link for our contract. Let's go ahead and verify that we're human, and we'll hit send request. This time, instead of sending us Ethereum, they're sending us.
I remember being kind of pissed off that I made a new wallet, unchecked it like he said, and then we had to go back and they were like, you can only do this once within 24 hours. So that's a thing that happened, I'm pretty sure. But hey, like we were at, I think we made it through 1 hour of video today, which is good. Maybe an hour and a half. We'll watch through. It's not 5 hours or 6, but let's see. If we are doing the official countdown tomorrow, and this was a 32-hour course, so it's like 4 hours a day, which seems more reasonable. Although I do know that it takes way longer than 4 hours to get through 4 hours of video. But let's just intensely try to get through this course starting tomorrow. And then it'll be done, and I will know how to program this, and I will have something that I can use as a portfolio to get a Web3 job. So, yeah.
10 test link, which is what's known as an ERC20 token, or more accurately, an ERC677. We'll get to understanding that a little bit later. We can see the asset in our MetaMask by importing the token. In order to get the token, we're going to come back to the documentation, and we're going to look up link token contracts, like that. We're going to go to the network that we just got the tokens on, which for us was Coven. We're going to copy this address. We're going to go to MetaMask, hit import tokens, paste that address, and hit add custom token, and then import tokens. And now we can see.
Okay, I wasn't paying that much attention, and no ifs, ands, or buts. Well, we decided we're not doing this anyway, so you copy and paste the address and then go to the thing.
In our account 1, we both have Ethereum and 10 link. Now that we have our link or our Oracle gas, we're going to send it to our API consumer. We're going to copy the address of the API consumer, open up our MetaMask, we're going to hit send, paste the address of our contract, switch the asset to link. For now, we'll just send 0.2 link. We'll hit next, and we'll hit confirm, and we'll wait for this transaction to go through. I chose 0.2 link because in this contract, there's a fee character, which tells us how much making an API call for this is going to cost. This one is actually 0.1 link. I sent 0.2 just in case we want to make that API call twice. Everything that's going on in this function we'll explain in a little bit later section, but for now, I just want to show you what it looks like to use. Once we send the link to our contract, we can first check to see what the volume is. The volume is 0. We want to get the volume of the last 24 hours of the Ethereum asset. We're going to be calling this API, which has a ton of raw data, including one in specific called volume over the last 24 hours, which is going to be this number right here. Say we want to get this into our contract from this API. We're going to make an HTTP GET call to this API. And what's going to happen is we're going to make the request in one transaction, and in a second transaction, the Chainlink node is going to return the value and store it in this volume variable in the global scope. So let's go ahead and hit request volume data. MetaMask is going to pop up. We're going to go ahead and hit confirm. And you'll notice right away, volume doesn't update. This is again because we actually need to wait 2 transactions. We're sending a transaction for the request, and then in a second transaction, the Chainlink node is actually going to respond. And after a slight delay, the Chainlink node has indeed responded with the result of making that API call back to our contract. We'll go over this process a little bit more in depth in later sections. The reason that I wanted to show you specifically the API calls is because we're going to show you a real-life example of how to use Chainlink VRF and Chainlink Keepers in a later lesson. Now, I know we've already gone over a ton, so let's do a quick review. In order to send Ethereum or whatever native blockchain token with a function, you need to mark it as payable. If you need something in your contract to happen, and you want the whole transaction to fail if that doesn't happen, you can use a require statement. To get the Ethereum or native blockchain token value of a transaction, you can use the global keyword message.value. Chainlink is a technology for getting external data and doing external computation in a decentralized context for our smart contracts. Chainlink data feeds or price feeds are ways to read pricing information or other pieces of data from the real world that's already aggregated and decentralized for us. Chainlink VRF is a way to get provably random numbers from the real world into our smart contracts. Chainlink Keepers are a way to do decentralized, event-driven computation. We can set some triggers, say, if this trigger hits, do something. And we get to define what the trigger is and what the do something is. Chainlink Any APIs is the ultimate customization of Chainlink nodes and allows us to connect to anything on the planet. To make this one production ready, we have to do the most work because it doesn't come already with a decentralized Oracle network like Chainlink Keepers and price feeds. We'll learn more about these Chainlink services as we continue in this course. Now, in order for us to figure out if our message.value is actually greater than the minimum USD that we set, we actually have to convert our message.value from its layer 1/Ethereum to the USD equivalent. So how are we actually going to do that? Well, first, we're going to need to get the price of Ethereum or Phantom or Avalanche or whatever layer 1 blockchain that we're working with. So let's create a function to get that price, to get that conversion rate. So we'll do function get price. And this is going to be the function that we use to get the price of Ethereum in terms of USD, so we can convert our message.value to USD. And then we're also going to do a function called get conversion rate. These are both going to be public functions so that we can go ahead and call them and test them and do whatever we want with them. So in order to get the price, we're going to have to use one of these Chainlink data feeds to get the pricing information. And we can look right here at this contract to see what using one of these Chainlink price feeds looks like. What we're actually doing when we're interacting with this Chainlink price feed is we're actually reading from one of these contracts. There's a contract out there called the aggregator contract that is a function called latest round data, which returns a whole bunch of data, but namely this int price. And this int price is what we are interested in. Let's look at our get price function and figure out how do we actually call this. Since this is an instance of us interacting with a contract outside of our project, we're going to need 2 things. What are those 2 things? We're going to need the ABI of the contract and also the address of the contract. So the address of the contract is going to be easy. We can get the address of the contract from the contract addresses section of the Chainlink data feeds. Let's scroll on down to RinkB, and we can find the ETH USD address on RinkB. And we'll create this contract so that it works on RinkB. So we're going to grab this address, we're going to copy it, and we're going to move back to our code here, and we're going to paste the address here. So great, we have the address now.
Oh no. We're going to docs.chainlink.com. Okay, so this is the address we are looking for. What are they talking about?
And we're going to move back to our code.
Oh, I guess we made these public now.
Here, and we're going to paste the address here. So great, we have the address now. We have the address of the other contract that we want to interact with. Now, how do we get the ABI? Well, what we did before with simple storage was we imported the entire contract into our code here. That's something that we could do, but that's actually a lot of code. So what's something that we could do instead? Remember, if we're looking at Remix and we look at one of the contracts that we compiled before, the ABI is really just kind of this list of the different functions and interactions you can have with a contract. The ABI itself doesn't actually need to include any of the logic. It just needs to include, hey, here are the different functions that you can call. For example, in this contract, we can call fund, we have get conversion rate, we have get price. They're not implemented yet, but they will be eventually. Now, there technically is another way to interact with contracts without the ABI, but for now, we're just going to ignore that. So how can we get the ABI? There's a concept in Solidity called an interface. And let's look at an example of an interface. If we go to github.com/smartcontractkit/chainlink,
I remember interfaces. I just put that in the wrong thing, but hey, we're super good. So good.
we can see a number of different contracts in the Chainlink repository. We can go to Contracts, SRC, v0.8, Interfaces, and we'll go to Aggregator v3 interface.sol. And if we look at the Solidity in here, we can see a whole bunch of function declarations, but none of the logic is actually implemented in this. This is what's known as an interface. If we compile this, we'll actually get the ABI of a contract because it defines all the different ways we can interact with a contract. It doesn't actually say what these functions do, which is fine though, because we don't need to know what the functions actually do. Those are going to be stored in the contract. So what we can do is we can grab this interface from the code and paste it into our remix. Now, hold on, if you're following along, you don't have to copy paste this with me because I'm going to show you an easier way in just a second. So for now, feel free to go ahead and just watch. But once we have this interface aggregator v3 interface, we can now use this to make API calls. So now we could say aggregator v3 interface at this address, and the combination of these two give us that aggregator v3 contract with whatever code is here. If at this contract address, this aggregator v3 interface is valid, we can do something like .version. Let's look at this interface. Is there a version function? There sure is. So that means we could call the version function on this contract. So let's actually go ahead and copy this into a different section. I'm going to create a new function called getVersion just to illustrate this. It's going to be a public, it's going to be a view, and it's going to return the uint 256. And we're going to split it up into two steps here, but we're going to say aggregator v3 interface price feed. So we're creating a variable of type aggregator v3 interface equals aggregator v3 interface at this address. And then we're going to return price feed version. Now I'm going to go ahead and deploy this contract to Rinkeby just to show you what this get version is going to return. But you don't have to follow along here if you don't want, because again, we're working with the testnet. You can just watch if you like. For this section, we are going to test a little bit more sparse, since we're going to be mainly using the testnet, since we're going to be working with an actual Chainlink Oracle network. Once we move over to Hardhat and with JavaScript, all this testing locally will be a lot easier and a lot faster. You're more than welcome to go ahead and fiddle and try and test a lot of the stuff as we go along, but just note that it might take a little bit longer to do some of the testing on a testnet. Let's delete that last Fundme contract. We're going to deploy this one. We're going to scroll up. We're going to switch to injected Web3. We're going to switch from Kovan to Rinkeby. And the reason we want to make sure we're on Rinkeby is because this address is specific to Rinkeby. The contract that we're looking to interact with might not be at this address on every single chain. We want to make sure we're on the Rinkeby chain for this, because if some other contract is there on a different chain, this version function obviously won't exist, and this function could error. So let's go ahead. We'll go to Fundme. We're going to deploy this to the Rinkeby chain. Again, you don't have to follow along with me here. You can just watch. And once that contract has been deployed, we now have a view function called getVersion, and we can see it's returning the variable for it, showing us that this is the 4th version of a price feed. So this is a really easy way for us to interact with contracts that exist outside of our project. We use one of these interfaces, which can get compiled down to the ABI, and then we combine that ABI with the address to call a function. As we work with these interfaces more and more, they'll start to make more and more sense. So if it's a little confusing to you right now, don't get discouraged. The more you work with it, the easier it'll become. Now that we know how to call these functions in here, we can start working with this interface. However, as you know, if we have a whole bunch of interfaces, we're gonna have to stick a whole bunch of interfaces at the top of our code, which looks pretty ugly. What's a better way for us to do this? Well, before we used import, right? We imported from simple storage.sol. For this one, what we could do is we could import from aggregator v3 interface.sol. We could go ahead and create a new contract with this aggregator v3 interface, or what we can do is we can import this directly from GitHub. If we go back to the documentation of these Chainlink data feeds, we go to using data feeds, we scroll down, we see at the top, we have this import statement. Import at chainlink/contracts/src v08 interfaces aggregator v3 interface. This import has the same path setup as the GitHub repository for the Chainlink code. Instead of us directly adding all of the code right into our remix, what we can do instead is we can import directly from GitHub, or what's called an NPM package. Remix is smart enough to know that at chainlink/contracts is referring to the NPM package at chainlink/contracts. We'll talk about NPM a little bit in the future. It's what's known as a package manager and can keep versions of different contracts for us to directly import into our code bases. At chainlink/contracts is created directly from the Chainlink GitHub repository. So Remix downloads this code from NPM, which is created from this GitHub. So now we know that if we import at chainlink/contracts src v0.8 interfaces aggregator v3 interface.sol, this is the same as if we had just stuck this whole contract right at the top of our Fundme contract, which makes our code look a lot nicer. And now we have this aggregator v3 interface that we can work with. Okay, great. So now that we have a minimalistic
I don't know what it is with me, but wow. Getting tired again. I am full of a lot of excuses. By like 411 pain. We'll try to stop at. I wanted to work a little bit more on finish my more of the metaverse, because we're not going to have a ton of time this week, and I need to sign my offer letter and deal with work and then start my new job, which is the same company in the different contract. It's fine. Everything's going to be fine with that. It's just going to be a really, really busy couple of weeks, and I thought that September was going to suck and October wasn't, but here we are. Yeah, so 10 more minutes, and then I'm going to hop into a space and do a little bit of our stuff, because we need to get this stuff done, and I need to write some things and get people into the registered properly, and do communications and get things written. There's some things I can do. I have to go out to my parents next weekend as well. So, like my whole, everything's everything. Everything is everything. But we can do this for another 9 minutes. Yeah, we'll do that. And I'm gonna go to bed at a decent time tonight. That way I can be, Little Miss Sunshine tomorrow when I'm like, hey, I actually read my offer letter and you are offering me less money to work at the same job. Not even in like a ephemeral sense of like inflation and I've been at the same salary, but in like total compensation. Anyway, here we go. 9 more minutes.
Interface, which will give us the ABI. How do we actually go ahead and get the price here? Well, documentation has a good example if you want to play with it.
So I think what they're saying is pretty much can just kind of copy this because it's from the example in the chain link and we're good. So it has the constructor, and constructors are run like before like as the class is loading, or the contract in this case. And you put the address in there, and then it's available.
And try to reverse engineer it as well. Here's how we're going to do it. In our code, we're going to create an aggregator v3 interface object called price feed.
So inside the get price, we have an aggregator version 3 price feed equals new probably. Let's see.
An aggregator v3 variable called price feed, which is going to equal to aggregator v3 interface contract at address, this address. Exactly the same as what we're doing down here.
Lol.
We're assuming a contract at this address is going to have all the functionality of this aggregator v3 interface, which again means it has this decimals function, this description function, version, get round data, and the important one, latest round data, which has the latest price at this answer piece. What we can do now is we can call that latest round data function on the price feed. So we'll say price feed dot latest round data. Now, if we look at the interface, we see that this latest round data actually doesn't return one variable, it returns a whole bunch of different variables. And that's what we're going to return in our contract. So we're going to put these parentheses, and we're going to say uint 80 round ID. We can even look right at the documentation to see what else it.
Oh, okay, so this was the thing that they have commas if you don't need things that are being returned.
Returns. Int price. uint started at. uint timestamp. And then uint 80 answered in round. Now there's a lot of code here. Since this function returns so many different variables, we have to set something up to capture them. However, all we care about is price. We don't care about round ID, started at, timestamp, or answered in round. So what we can do is just remove them and just leave the commas. Now we have int price equals price feed, that latest round data. The reason that price is an int 256 and not a uint 256 is because some prices or some data feeds could be negative here.
Price can be negative.
So that it's an int 256 so it can stay flexible. Now that we have the price, this is going to be price of ETH in terms of USD. And we saw an example of this before. It was around 3,000 and it returned this number because Solidity doesn't work with decimals for a number of reasons, but we just need to know that there are 8 decimal places associated with this price feed. If you want to double check how many decimals there are, this contract has a decimals function that you can call as well that will tell you exactly how many decimals are in this price feed. Now, as we know, message.value is going to have 18 decimal places. Why does it have 18 decimal places? Well, because 1 ether is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8 is this massive number in Way, which has 18 zeros, which is equivalent to 1.1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. So we want these to have the same decimal places, right? Because right now this has 8, this has 18. They're different units right now. So to get them to match up, all we need to do is return price times 1E10 or 1. raised to the 10th, which is equal to 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Message.value, though, is going to be a uint 256. And right now, price is an int 256. So why do we convert this value from an int 256 to a uint 256? Well, we can do what's called typecasting. All we need to do is add uint 256 and wrap this whole thing up between these two parentheses. You can't typecast anything, but there are some values like int256 and uint256 that can be easily converted between the two. Now, of course, since we're not modifying any state with this getPrice function, we can make this a view and say it returns a uint256. And if we save and compile, we go ahead and we get that check mark. Now, math can be a little bit tricky the first couple times you do it in Solidity, but the more you do it, the easier it becomes. And in the future, we can always reference a function like this to figure out, okay, here's the easiest way for me to get this number. Awesome. So now we have a getPrice function, which is going to return a uint256, which is going to be the price of Ethereum in terms of USD. All we need to do is convert the message.value from Ethereum to terms of dollars. Let's create this get conversion rate function. For this one, we're going to take an input parameter of uint256 of ETH amount. It's going to be a public view function, and it's going to return the uint256.
Is it return or is it returns? I'm pretty sure it's with an S.
We're going to pass it some ETH amount, and on the other side, we're going to get how much that ETH is worth in terms of USD. So we're going to do a uint256 ETH price equals getPrice. So first, we're going to call our getPrice function that we just created to get the price of Ethereum. Then we're going to do uint256 ETH amount in USD equals.
Okay, so
ETH price times ETH amount, and then we're going to divide by 1E18. When you're doing multiple
does say public view.
Multiplication and division math in Solidity, you always want to multiply and add first, and then go ahead and divide. Since ETH price and ETH amount both have 18 additional decimal places, if we were to just let them rock without this, they would have an additional 36 zeros tacked onto the end. So we need to divide by 1E18. Now, when we get to the hard hat sections of this course, testing all this math is going to be a lot easier. And if you're really struggling with some of the math bits right now, I wouldn't let that slow you down, because once we get to hard hat, it's going to become a lot easier to actually test this than working on a test net. And this ETH amount in terms of USD is the number that we're looking for. So we can just go ahead and return ETH amount in USD. This needs to be returns here, and boom. Now we have a get conversion rate function. To walk you through the math real quick, let's say the ETH price is going to be $3,000. So it's going to be 3,000, but it's going to have an additional 18 zeros tacked on the end. It matches the message.value way units. And let's say, for example, we send 1 ETH, or 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8 ETH into this contract. 1 ETH should equal $3,000. So to get the price, we're going to now do the ETH price, which is 3,000, times the ETH amount, which is this 1, and then divide by 1 raised to the 18. So math it out, we'll do 3, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8 times 3,000, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 1, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now we divide that by 1, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which equals 2.99999E21, which the calculator kind of messed up the math a little bit, but 2.99E21 means this has 21 decimal places. So it'd be 2.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1. Or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8. 2,999.9999999. And this is actually exactly the reason why we don't do decimal math in Solidity. Our calculator saw that massive number, was having a hard time getting it, so it ended up rounding that number to 2.9999999. When we work exclusively with whole numbers in Solidity, we don't have a chance of losing that precision. And in Solidity, this is going to return exactly $3,000, which is correct. 1 Ethereum at $3,000 per Ethereum is going to be $3,000. And like I said, since we're building this contract, assuming we're going to be working on this testnet, we're not going to test this function on the testnet because we're going to have to wait for that transaction to go through. If you want to go ahead and deploy this and play around with it yourself, you're more than welcome to. Okay, great. Now we have a function called get conversion rate that we can use on our fund function to make sure we've sent enough message.value in our fund. So what we can do now is all we need to do is do get conversion rate of message.value needs to be greater than the minimum USD. Of course, right now our minimum USD is just in terms of 50, and we know that get conversion rate is going to return it with 18 zeros to represent the decimal places. Our minimum USD amount needs to be upgraded to 10 to 50 times 1E18, or again, 1 times 10 raised to the 18th. I'm going to deploy this to a testnet just to demonstrate it, but again, you don't have to if you don't want to wait for this. So I'm going to go ahead and deploy this, confirm, and
Yay, we made it to 420.20. So this is a good place for me to stop. It is 11:24. I am not doing the metaverse tonight because it is my bedtime. I should probably not even try to find any thing. I'm gonna look for that person's message because I think they want to give me a prize, and I was just kind of blew them off because I have things I need to do. So anyway, thank you for sitting through this stream with me if you have, and we will get through this Solidity course together. Yeah, we need to get this over with the next week, 4 hours per each. I'm gonna go ahead and say that it's not possible for me to finish this within 1 week, but we'll be way further along. And every day that I try, and I do at least a little bit, is a day closer to me actually achieving my dreams of working part-time, doing something while I do my main project, which is banned books art. Which actually, I guess you would say that my dream is to just do banned books art and not have to worry about, doing contract stuff and other projects, and just be solely focused on me. But I do enjoy owning a house and having cats and being independent, so we need to be able to eat. But this is a step in the right direction for me, so I will talk to you later. Thank you so much, and I will see you tomorrow.